Hello, my name is Michael Paloian. I'm the president of Integrated Design Systems. I'd like to thank Informer for inviting me to share this presentation with you. Presentation is entitled Top 10 Most Important Injection Molding Design Considerations. And this was actually based on a paper I wrote for them a couple of months ago, which really is a result of my experience designing injection molded parts for the last 40 years. I'm president of Integrated Design Systems. We're located in Oyster Bay, New York. And I've essentially been involved in the plastics industry uh, since my early 20s. I graduated from UMass Lowell with a degree in Bachelor of Science in Plastics Engineering, and then I got a graduate degree in industrial design from Rhode Island School of Design. And throughout my 40-year career, I've been involved in the design of literally hundreds of different products from inception to completion, many of which were injection molded. And I've personally experienced everything that I've covered in this presentation. And hopefully, I will help you benefit uh, in your experiences going forward when you're designing your products in your careers. Before I get into that, however, I'd like to first of all identify one of the most important steps before you begin a project, and that is specifying the requirements for a product. And in defining these specifications, depending on a project or the product, you may include industrial design requirements, which include aesthetics, branding, and a number of other parameters that are specifically important to industrial designers. And this of course will affect the product design. In addition to that, in these specifications, you should include a comprehensive description of the product's purpose and function. And this is sort of an obvious but important consideration that should be defined. Then there are the user requirements, which affect ease of use, safety, and convenience for the end user. And these are typically fall under the umbrella of ergonomics, another significant design parameter that should be included in the specifications. And then there are the environments of use. And these typically could range from chemicals, which might be used to clean or come in contact with the product, especially plastic products, and radiation, impact strength, uh, electrical resistance, thermal properties. There are a number of environmental considerations that should be defined based on the intended use of the product. Then there are other parameters which pertain to storage, shipping, and warehousing. Sometimes products are shipped in disassembled and they have to be assembled on site. In other cases, they have to withstand temperature extremes during warehousing or storage, depending on where they're stored. In shipping, you have to often design products so that they can withstand the vibration and typical handling during shipping and transport. In addition to that, the specifications would also include regulatory requirements, whether domestic or international. And then there's the reliability and performance requirements of the product, especially for extended warranties or periods of use. And then you should document the marketing and sales requirements, which impact the sales and success of the product in the marketplace. So once these specifications are defined, now you're getting into the execution of how they'll be interpreted in the design, especially if it's for an injection molded part, which we're going to be focusing on. The top 10 injection molding considerations after you've defined your product specifications include material options and the consequences related to that material selection. There are hundreds of thousands of plastics to select from, and selecting the ideal plastic or group of plastics in that huge pool of options is extremely important in any injection molding project. In addition to that, another major consideration are the critical tolerances. Depending on the materials, the process conditions, the design, this is always a challenge that's faced by all engineers and designers when you're designing injection molded products. Then there's, of course, the potential of sink marks and how to avoid that. Always a challenge for designing injection molded parts. And in all these cases, it's always wise to reach out to a molder that you trust or that you're uh, dealing with in your supply chain and confer with them throughout the design process as you start refining these features. In many cases, it's difficult to predict how parts might fit together, especially when the tolerances are very tight. And in these cases, it's always better to design the parts to be slightly loose fitting, okay, which means that the mold has extra steel in it. So the parts are a little smaller than they should be, depending on the features, of course. And that's what is implied by this term steel safe. It's easier to remove metal in a tool than to weld it in and start to remachine it. So another consideration that we'll be talking about. Then there's gate location. And this is an important factor which is oftentimes overlooked, but it could cause problems down the line when products are molded and trimmed for final assembly. And another key injection molding design consideration. Shut-off angles. Providing adequate draft angles in features that are created by a shutoff, which I'll describe a bit later, is critical to maximize tool life and to avoid galling of molds and experiencing excessive flash in parts. Draft angle orientation is another important consideration, sometimes overlooked. And depending on how that draft is directed, you could end up with a fit problem in a part or a part not functioning properly. So that's an important consideration. There's texturing in draft. If parts are textured with certain etched textures on for cosmetic reasons, this will affect the draft angle and also actually change the part geometry. Another major design consideration. And then there's something that's often overlooked, and that's scheduling of how parts are ordered during production startup. If you order everything at the same time, if you're ordering tens of thousands of parts that are essentially going to an assembly, and the first samples are slightly out of spec, and you can't meet the tolerances, now you've got yourself a problem. So we're going to talk about the critical phases of startup and how to avoid those kinds of issues. And then there's secondary operations and fixtures, which is another major consideration for designing injection molded parts. So in terms of material selection, we have parameters to take into account. Regulatory compliance. Sometimes materials have to be flame retardant, or they have to comply with minimum toxicity, or they have to comply with certain impact requirements. So these will help narrow down the field of or the options for your plastic selection. Then there's chemical resistance. Some plastics have poor resistance to alkalis or chlorine or solvents. So understanding the use, as mentioned earlier, and the chemical resistance of the polymer to the chemicals that will be exposed to it is extremely important. And often this information is not uh, very clearly defined by resin manufacturers. So it may require some testing to verify the performance of the resin. There's temperature resistance. And again, another parameter or property that's with for plastics difficult to define because the heat distortion temperatures doesn't necessarily equate to the maximum use temperature of the plastic, especially when it comes to plastics under load. So a temperature is a major consideration. Then there's impact strength. And this is essentially the energy required to fracture the plastic. It's dependent on the resin as well as the design. So if the design minimizes uh, induced stresses during molding, if you have generous radii in your part will perform a lot better under impact conditions than if it has sharp corners or has a lot of molded in stress. Then there are long-term properties such as creep, fatigue, and wear resistance, for instance. And these could be either evaluated. Some of these could be evaluated under simulation or again physical testing. And toxicity, as mentioned earlier, another especially for medical applications. There's UV stability. And sometimes, even though a product may not be used outside, fluorescent lighting and just ambient lighting through windows could cause discoloration in the plastic or loss of impact strength over time. And then there are electrical properties. If there's high voltages involved, the dielectric constant, dielectric strength of the materials are an important consideration. In addition to the physical properties that I've just outlined, one should also be cognizant of the application and the product requirements, as mentioned earlier when I was citing some of the parameters associated with specifications. And again, regulatory requirements, safety requirements, cost constraints. Okay. Then there's processing considerations. All these parameters affect material selection. Availability. Today, this is a major concern. Many plastics are in short supply, and the lead times are, quite extensive, sometimes months. And availability is a major, especially today, a major concern. Then there's lead time, and which goes hand in hand with availability. And then in many cases, especially with the pressures being applied to manufacturers today, materials ease of recycling after its use, after the life of the product has been completed. And then when you get into certain specially formulated compounds, or some of these could be include special pigments or additives for stability. There's typically a minimum order size. So another consideration when you're defining a material. So once your material is defined, of course, all these things are not done sequentially, they're done concurrently. Critical tolerances are another significant parameter for designing injection molded products. And it's quite challenging because there are guidelines that manufacturers publish for recommended tolerance ranges for plastics, but often tolerances for applications have to be much more tightly held than what's published. And designers should be aware of those parameters affecting tolerances. And these include the type of plastic that you're molding. For instance, there are plastics be categorized based on their uh, chemical structure. There are semi-crystalline plastics and there are amorphic plastics. And depending on the type of plastic that you're specifying, the shrinkage rate can vary substantially, and the way the material shrinks uh, will uh, will be determined by its chemical structure. Amorphic plastics tend to shrink isotropically, meaning the same in all directions, whereas semi-crystalline plastics tend to shrink anisotropically, or they shrink differently in a direction of flow versus the transverse direction. So they're more prone to unpredictable behavior in terms of how those parts uh, how the tolerances are maintained in production. Then there's the tool quality, which is dependent on the steel, the gate location, cooling lines, and of course the machine tolerances, because your parts are not going to be any better than the accuracy of that mold. So tool design and construction craftsmanship are extremely important when it comes to tolerances. In addition to that, there are your processing parameters, which include cycle time, the mold temperature, the injection pressures, the uh, the tonnage used to clamp the part during the cooling cycle. All these parameters will affect the tolerances in a part. And then there's part geometry. If your wall sections vary a lot in your part geometry, you're going to have a more difficult time maintaining or controlling tolerances than if a part has a uniform wall section, which is really preferred for injection molded parts. Not always easily maintained, but always a preference. And in addition to that, if a part has a lot of features in it with holes and complicated openings, it changes the shrinkage and stresses induced in a part and could affect the tolerances, especially for semi-crystalline materials. The material properties that affect tolerances all include the modulus elasticity. In other words, a rigid plastic with a high modulus above 400,000 psi, for instance, would have a typically a lower shrinkage and a higher repeatability during molding than a lower modulus material like polyethylene, for instance. Then there's, again, what I mentioned earlier, the chemical structure of the plastic, whether it's amorphic or semi-crystalline. It's the material's viscosity, which is a function of its molecular weight, is another parameter that will affect tolerances. Its chemical structure, fillers versus powders, because when you get into materials that are like glass reinforced plastics, for instance, there's an orientation to the fiber ratio of length to diameter, which will change the rigidity of the plastic as it flows through the mold and also alter its shrinkage and ultimately its tolerances, versus a powder or a filler, which is symmetrical all the way around. It's essentially a sphere. And the fillers tend to essentially occupy volume and improve the repeatability of the tolerances during manufacturing. This is typically done with polypropylene, for instance. They often add fillers to improve its moldability. So, as far as tool quality is concerned, you've got overall precision of the machine features to contend with. These are out of the control of a designer, but things to take into account, especially when you're dealing with a molder. You can discuss these requirements for your product. It may dictate the type of tool that they specify for your application. How the cooling lines are run through the tool is another key parameter affecting tolerances, heat distribution, etc. Then there's gate location and design. whether it's a fan gate or an edge gate or a sub gate. We'll talk about that a little bit later. All these things will affect the tolerances and the length of flow of the material. Surface finish of the part and the type of steel that the tool is made in all affect the tolerances of a part. When you get into when you start looking at the processing parameters, you've got mold temperature distribution. In other words, you have a core and cavity, and or you have fine features in very, thin blades of steel that are so coring out certain features. These may affect how that part is cooled, and it could affect the tolerances of the features as well as the overall product. There's the injection pressure profile, the cycle and cooling time, the injection speed. In addition to processing parameters, you've got part geometry. And this is where you, as an engineer or designer, have to be aware of the fact that part tolerances are a function of part size and part length. The longer the part, the larger the part, the greater the tolerance you have to allow in your design to have that part comply with your specifications. So the tolerances are typically defined for plastics as plus or minus X number of inches per inch or X number of millimeters per millimeter. And that has to be considered during your design, the clearances you provide in your parts and the fits that you're expecting from part to part. In addition to the size of the part, the when a tool maker is designing the mold, what they're doing is they're taking your CAD file and they're actually enlarging it by a certain percentage based on the shrinkage rate of the material. And this is an estimate, and it's a uniform enlargement of the product. So it might be like anywhere from 0.05% to a 0.5% or even 1%, depending on the material shrinkage. And so this is a guess. And what can happen is certain areas of the part may shrink based on the allowance that the tool maker has allowed, or they may shrink less or more, and that's why you get your tolerance variation. And once that's experienced, the parts are now molded fairly consistently if the processing conditions are maintained from part to part. So it's that initial shot that is critical. And as mentioned earlier, the tolerances can range anywhere from plus or minus a thousandth to as much as 15 thousandths of an inch per inch, and that's quite significant. Typically, the olefins tend to have that higher shrinkage rate. And another factor, as I mentioned earlier, that affects the tolerance variation is the uniformity of wall thickness. So if you have a lot of variation in your wall thickness, certain areas of your part during cooling will cool more slowly than others, and it's going to affect the molded in stresses and also the consistency and how those parts are molded from shot to shot. Sink marks are one of the greatest challenges for engineers and designers when they're designing injection molded parts. And although the rule of thumb is quite simple, the application is not that easy. So the factors that affect sink marks are the ratio of intersecting walls, meaning if you have two walls, one wall perpendicular to the other, the ratio of I'll call it a rib to the fascia wall should be anywhere from a half to 60% that of fascia wall. That's your limit, 60%. That's the guidelines. Now, it's as you start to deviate from that range, you're going to start to experience a certain amount of surface sinking, because the material is actually cooling at a slower rate, and it forms a skin, and then it starts to actually shrink in, and you get a sink mark. That's what causes the shrink mark. So that's also a function of material shrinkage. Some materials tend to shrink more than others, as I mentioned earlier, and they're more prone to sinking than other materials. Then there's the wall thickness. If you have a very heavy wall, it's going to take a long time to cool. You can get some irregularities in that wall, and you're going to get um, an aesthetically unappealing surface finish. And then there's the tool design. Okay, so all these factors affect sink marks, and in addition to that, you've got gate location. So the longer the material has to flow and it starts to lose pressure through that long flow length, it's going to not pack out in the tool as well, and you're going to get a higher propensity for sink marks, depending on how the materials are flowing apart. So if you're designing something and your fascia wall, which you see in a horizontal axis down below, is about the same thickness or thick as a rib, which is typically on the back side, the material is going to tend to sink in. You're trying to keep a uniform wall section. When you start having these kinds of geometric features in a part, you start deviating from that ideal requirement. So the idea is to keep that rib thin to as much as 50 to 60% max of the appearance wall to avoid any type of surface blemish. And you can see in the illustration on the right how that's achieved. And that has to be thought of in three dimensions. You can't just think about it in one axis. You have to think about it in all the intersecting planes that rib is attached to or derived from. If you're designing parts that have to comply with very stringent tolerances, typically way beyond what is normally held or what can be normally held by the average molder, it's always good to design those features steel safe, as I mentioned earlier. And what that means is you're providing a few extra thousandths of steel in those critical features, which may be eventually ground away after the first shots are taken to tighten up those fits later on. So when you have extra steel in a mold, that means the part is that feature is going to be a little bit smaller than what it would normally be. So you're intentionally making that part, like let's say it was a snap fit, slightly loose, and then once you take your first shots, depending on how the tolerances fall, you can go back and tighten it up later on. And as you see in this illustration, the clearance that has been provided in this particular feature, this is an actual part that was developed. You notice there's clearance in this part. And theoretically, you would expect that part to be loose fitting. And in some cases, it could be, depending on how the tolerances stack up. But it's better to have it designed this way than to have it too tight, in which case that steel would then have to be to modify the fit. You'd have to weld that steel back into the tool, which is a lot of work. It also diminishes the life of the tool. And now go back and machine it and get it to fit properly. So this is what is wise when you're designing critical fits. It's always easy to take the metal away and tighten up your tolerances. And it's something to keep in mind. It's something to apply when you talk to your molder or tool maker. So it's always good to network with your partners in any project, so everybody understands the design intent. Gate location is critical, not just in the cosmetics of a product, but it has many other critical implications. So a designer should always be aware of the type of gate that's being used and its location. And I'm going to give you some examples of what I mean by gates. Okay, there's a sprue gate which you see here, and in this case, you've got a sprue coming down, feeding through runners and down to the individual parts in what's typically done in a three-plate mold. Okay, then you got an edge gate, which is a typical two-part mold, where again you've got a sprue feeding a runner and it goes into the edge of a part. So if you're designing something that's cosmetic and you don't want to have a little mark on the outside of a part, you can't tolerate that, then you can't use this type of a gate. It's going to that has to be trimmed off, and it's going to leave a visible mark on the outside of the piece, which if that's a problem, would have to you'd have to gate the part a different way. Then there's a fan gate, and fan gates are often used to maximize the uniformity of flow in a part. It's ideally suited for lenses or windows for displays, etc. Because you have a very smooth laminar flow throughout the uniform flow throughout the entire cavity. Now, the disadvantage of a fan gate is it has to be trimmed off with some sort of a cutter, a saw, or what have you, to so the removal of that gate is a lot more labor intensive than, for instance, an edge gate, but it gives you a much better cosmetic part, especially when it comes to optical clear windows. Then there's a hot tip manifold, which is ideally suited for a lot of small parts, where in many cases the runners could weigh more than the actual parts, and all you'd be doing is regrinding plastic and molding it over and over again. So hot tip manifolds are great for multi-cavity molds where you're molding a number of smaller parts, and you want to have a great yield on your manufacturability. Then there's a subgate, and the subgate is automatically stripped from the part during ejection, and these leave a very, very tiny mark on the outside of the surface. And then there's a runner like you see here, which is feeding into numerous cavities for a multi-gated part. So bear in mind that this gate, although it seems like it's trivial, it affects how the moldedness stresses in the part. It affects how the wall thickness of the part. It also affects the fit of that part to another piece. So here's an example of why designers and engineers should talk to the molders to get a consensus on how they envision that part to be filled. This particular camera housing or scanner housing was designed with 4 edge gates with a center sprue, and you can see the images to the right, which are close-ups of the little residual material that's left in each of those gate areas, and that provided a uniformity of flow throughout that part. And then those features had to be machined off later on so as not to cause an obstruction with the mating piece that fit into that window. So this is what I'm talking about when it comes to being aware of where the gates are and understanding how they're going to be trimmed and specifying that to the molder so that when parts are ultimately assembled, there are no problems during the assembly and performance of the product. And also, this provides a part that, by properly gating it, you're, again, as you remember, optimizing the tolerances and the overall features of the part during processing. A technique that's used often for creating complex shapes, especially openings or what would otherwise be an undercut in the part, is the use of what's called a shutoff or a bypass in a tool. And that's achieved by essentially having the two halves of the mold, referred to as the core and cavity, uh, essentially kiss off on a surface. And right through here, you'll notice this represents steel coming up from the core side of the mold, and the cavity comes down and shuts off on that, and that is called a shut off angle, and that provides an opening in a part, this opening here, and it allows us to mold this overhang without putting a lifter in the tool. Okay, otherwise you'd have to have a slide in a mold, which in this case would not even be possible to create this feature. So this technique allows you to create some very multifunctional, complex parts with highly reliable tooling at minimal cost. But the key is to design the feature so that it complies with this requirement of a 3-degree shutoff. 3 degrees is minimum, okay? 3 degrees to 5 degrees or more is always preferred by molders. But obviously, when you're designing something, the greater you start increasing these angles, you start running into other problems. So the minimum is really what I'm emphasizing here. You don't, if you start going below this number, you go down to 2 or 1 degree. Now you start running into a potential for galling of the mold or flash in the part, and and by maintaining this angle, you're providing a high degree of pressure on that surface, and basically eliminating any potential for flash, and also maximizing the tool life. So this is surprisingly not done that often, and in many cases, the tool life is shortened, and the parts tend to come out with a lot of flash or uh, warpage, for ejection purposes. So you don't want to have a 0 degree steel on steel uh, feature here, which is critical. So this complicates the design quite a bit, but by doing it, you're as I mentioned, increasing the tool life and maximizing the quality of the product. And something to keep in mind. Number 7, draft angle orientation. This may seem like a trivial point, but it's not. Because when you're designing injection molded parts, you have to add draft, as you all know. And the image you see on the right shows a pictured, three-dimensional image of the cross-sectional piece on the left. And that green represents the cavity side, the red represents the core side. And this is a draft check that was done using SolidWorks. So what you're seeing here is the draft running from the cavity down. So if your cavity has a core pin that comes down to mold this feature, that means that the bottom of this is going to be smaller than the top. So if you have something fitting in here, it's critical to understand that, because you may, if you have something that's partially fitting down to the halfway point, or there's I don't know, some other functional requirements in your design that requires this orientation to be defined, you want to know that the draft is running in the correct direction. Because if it's coming up from the other end, which it could, in this case, the core could be coming up from the middle, okay, and it could be reversed. And if you're trying to fit something to that product, then or that component, you may run into a fit problem. So it's always important to know which way the draft is running, and also it affects the tool complexity. Sometimes it's better to talk to your tool maker to see if they might prefer to have the draft running in another direction for sake of simplicity of the mold and saving tooling costs. The So in this case, as I mentioned, the stand you have a core pin that's coming down, molding this feature from the cavity side, and in the other cases, these shutoffs in here and the holes you see in the bottom are all coming up from the core side of the tool. So all those features are on the other side of the mold, and that was the molder's preference. That's why that was done. In this case, it was necessary, but in this other case, it was uh, the molder's preference. So the direction of draft affects the part fit, the tool design, and the tooling cost, an important consideration. Texturing and draft. Sometimes parts are designed with a fairly heavy texture and they don't have enough draft, and they're not molding properly. So a good rule of thumb to keep in mind is to when possible, design your parts with a minimum of 1 degree per side of draft. That's sort of the injection molding 101. But if you start adding texture to a part, and that texture could be a bead blast or an etch texture, it doesn't really matter. What you're doing is you're, in essence, adding all these little tiny undercuts to the surface, and that's what you see here. So by increasing the draft angle, you're allowing the steel to sort of eject from those undercuts without having it rip off the feature above it, which actually results in these scuff marks on the surface of the part. That's why uh, companies like Moldtech, for instance, recommend a 1 degree added draft for every thousandth of an inch of texture depth. So if you have a texture that's 5 thousandths deep, you want 5 + 1 or 6 degrees of draft minimum to eject that part. So that's gonna actually change your part geometry. And you can see, like this simple box, you've got 2 mils of texture. This is what the box would look like versus 7 mils of texture. And the box is going to change to this very, dramatic trapezoidal shaped, overall shape. So it'll have a big impact on the root geometry of a part. It's important to really decide that up front when you're designing something and consider that texture in the very beginning of your design, because it'll have a huge impact on all the features you add to that design going forward. When you're finished with your design, when you think you're finished, you're partially finished, because now you have to face the last phase of your project, and that's really the production startup, when you're looking at the first articles coming out of the press. And when you're going through this critical phase, very critical phase of a project, you're going to be looking at and inspecting the part from an aesthetic point of view. As you see here, certain processing problems were highlighted and brought to the attention of the molder to define the overall expectations from a quality standpoint, what's expected for them in an ongoing basis once they get into production, so that everyone is satisfied with the final product, what's reasonable for them to maintain and what is reasonable for the company to expect going forward. Then there's, of course, a dimensional inspection, and these dimensional inspections are not as easily defined as what you see in this overly simplistic image here, because plastic parts tend to warp a little bit, and if they're not, especially larger parts, so if they're not measured properly, you can end up getting deceptively erroneous measurements, which could cause a lot of misunderstanding in terms of why the parts are not fitting together properly. And the last thing you want to do is go back and start making changes without really getting to the root cause of a problem. So this is a critical part of this startup phase. And then you want to verify that all the parts that are going to be assembled, whether they're sheet metal parts or PC boards or whatever you have going together, that they're all fitting together properly. And you don't want to order all these things at the same time, because if you ordered, let's say, 5,000 PC boards and they're already made and they're in inventory, and now the molder can't, they find that the molded parts are out of spec, and it's going to be cause a major tooling change to revise the tool to change, let's say, boss locations, etc. And it's going to be very expensive. Let's say you made a mistake. Many reasons to take into account here. It's easier to change the whole location of a PC board versus changing a tool. So if you don't order all the PC boards at the same time and you have the benefit of evaluating its fit to the part early on in this production startup phase, you can always modify the PC board and then order them to comply with the part. This is some companies frown on doing something like this, but it's a reasonable and sensible alternative to delaying the project or going through some costly tooling revisions. So that's what I mean by critical startup phases. And then there's a functional evaluation. You want to make sure that that part is performing according to your expectations, especially if you design something with, like in this case, elastomers. You want to be assured that the feel, the elasticity, the flexibility of the part performs it with your expectations, and you don't order 10,000 elastic overmolded parts to find that they're all too stiff. You want to make sure that the feel and aesthetics of that product perform in accordance with your expectations. And the last of the top 10 considerations that should never be overlooked are the secondary operations and fixtures. And these I've sort of segregated two categories: assembly and decorating. And in the area of assembly, there's bonding, which is in itself an extremely complicated topic, because you've got so many parameters associated with bonding, which we don't have the time to get into. But the choice of adhesives, how their viscosity, their chemical resistance, how they're applied, their curing times, all these things are critical in determining how a product should be assembled. Then there's the potential of welding parts, especially semi-crystalline materials, which are difficult to bond, like polyethylene or nylons, it's acetals. These materials sometimes are difficult to bond, so they're more easily welded together, and if it's possible. And the welding could be done either by literally using a hot air gun, or ultrasonic bonding, or spin welding, or hot plate welding, all these different assembly methods. Then there are fasteners. Now, this is the fasteners are interesting, because if you think about screws, which are the most common type of fastener, often plastic products are designed without any specs on how they're assembled, and specifying the torque levels of the screws is really important, because you could either overstress the assembly and potentially strip the screw out, especially if it's a self-tapping screw, or you can induce too much stress in a part and cause eventual failure in the field. So there are requirements and parameters to specify when you're defining the torque levels of a screw during assembly, and I strongly recommend that because it is a primary consideration to avoid failure in the field. And then there's, of course, in terms of assembly, the part geometry. And what I mean by that is, your parts could be designed to snap together. Um, you might want to orient the part so that everything is built from, the base up. So you don't have to keep on turning the part around for every different component that's assembled to it. So all these are important considerations for the assembly of a product. And in the area of decorating, you've got paints, and paints have to be compatible with the substrate and the surface preparation of the part. So the parts have to be cleaned and devoid of any type of uh, release agents or contaminants on the surface, so you get a nice, clean, uniform paint finish. This plating is another decorative, commonly applied method of decorating plastic parts. Um, Pad printing, and pad printing, although it's very versatile, the alignment of all the colors and how the parts fixtured and held in a pad printing press is a critical uh, consideration in your uh, documentation and in your overall design for an injection molded product. And of course, silk screening, which is really ideally suited to either cylindrical or flat surface. You can't go over a compound surface with a silk screening operation. So again, that affects the part geometry. So my closing remark here is you want to coordinate with all project contributors from the very beginning of a project throughout the entire development process to the final approval of that first article. And depending on what phase of the project you're in, you'll be dealing with, of course, different individuals or entities. And my advice is that the molder and the tool maker should be a key partner with you from the early stages of the design right up into the first article approval. And in addition to the toolmaker and molder, you've got marketing people, you get your purchasing department, your manufacturing engineers, your service department, and of course your tool makers and molders. That essentially concludes my presentation. I hope you found it interesting, and I want to thank all of you for attending.